the beautiness of the ugliness of semiclassics, and of course getting your feedback. And on top of that, you know that talks are very fermionic, so you can pass one idea or none, but never two. So that's why I decided to concentrate on that thing. So on one hand is, what is the motivation? Well, I'm a condensed matter physicist, so I've always been trying to link the quantum chaos with things that can be measured. And in this case, the motivation is a little far away. So it comes from this holographic duality. So I'm kind of modest enough to go to my high energy colleagues and say, give me a 101 introduction. And this is as much as I understand, which means I don't. But anyway, so what they tell me is that, so if you have a theory which is with quantum gravity and the Holy Grail, the whole thing, so this holographic duality allows to map into the boundary or something that is a conformal field theory, and this is much easier for them because they say it's a flat space-time, and they can do things. The way they use these analogies, if they have a problem, like here, for instance, in their case was physics of black hole, they can do the mapping, make calculations in here, and learn something the other way around. Okay, how was in this particular case? Well, now it's, when it comes to the name of Maldacena, who has been related not, I mean, he has also worked with that, but more specifically in this case, he says that in order to understand problems in this domain, right, it's useful to consider this object, that it's a correlator of, it was interesting, for instance, Marcos said yesterday, this is the norm of an operator. I don't tend to think in that term. You can think it in different ways. But you have a commutator and the complex conjugate, and you do the thermal average. Okay? So what's the interest in this thing? Well, there's the prediction that this object is going to increase in terms of h bar. That's very important, certainly, and exponentially with time. Of course, when these people, high energy people, saw an exponential with time, they call it Lyapunov exponent. And we will see whether or not that's appropriate. And moreover, they put something which they call a bound of chaos. So they say that this growth rate, let's call it like that, it's bounded by the temperature, in a way. Of course, we have to go back to the things that we know how to do, which are, all, you know, all here in this audience, that this is our kind of typical domain, which is rather far away from there. And somehow the idea is that here when they do the mapping, they say, well, it's in strong coupling, so which means many particles. We don't. We are going to work with one particle. And so that's why there's there's quite a discussion now, or what is the relevance of this OTOC. And for instance, Maldacena says that for condensed matter, he's a bit surprised in the sense that exploded that way, because it's not what he meant to do. I mean, I'm going to take for once the approach of quantum chaos and say, in one thing that interested us is the analogy with a problem we have worked for a while, which is the LOSCHMIT ECHO. So this is, I mean, this is something that we immediately realize. So just a transparency to remind you, I'm sure many of you have worked on it. It's probably useless, but nevertheless, so what's the idea there is that you have a quantum state, you propagate with a given Hamiltonian, you propagate with a Hamiltonian that is slightly different, you call environment the difference, and therefore you ask the overlapping between these two states, which is what you call LOSCHMIT ECHO, and this is in the kind of fidelity version in which you study the sensitivity with respect to this small perturbation. However, in the way of echo, it's more that you propagate with a given Hamiltonian, you propagate it backwards with a slightly different Hamiltonian, and the question is, okay, what is that? Well, I'm simplifying enormously the thing, but somehow we came up with my good friend Horacio Pastaski a long time ago to say that with using semiclassical approximation and sort of avoiding prefactors and all that, we can say that this essentially for weak coupling is dominated by something that depends on the environment, and after a critical coupling, then this term is no longer there, and the decay rate of the LOSCHMIT ECHO is dominated by this L, which is indeed the Lyapunov exponent related with H0. And this is sort of relatively surprising in a way. But then, where is the analogy? Where is the things that are not that close? Well, in the OTOC, in the way you see this correlator times the complex conjugate of the correlator, essentially has a few terms that we are going to look after, and you can interpret as the overlap between taking a state, evolving, sort of taking an operator in Heisenberg representation and evolving it, and using this guy as a measure, let's say, or doing the things in the opposite order. So in that sense, there is an analogy that we would say, well, for a semi-classical guy, it's clear that this has 4 trajectories, and 4 trajectories is going to be in the case of the OTOC as well. Actually 5, because we have temperature. That said, I think I'm not going to enter that much in this detail. There's last week a preprint by Zurek on the analogy. I think that the analogy perhaps has to be taken with some caution, because it's clear that in the LOSCHMIDT ECHO we have 2 Hamiltonians. Here we have just 1. And moreover, if you think about the classical limit, so it's clear that this experiment, which actually comes from spin echo, and that was the reason why we come, is perfectly doable at the classical level. You can propagate back with a small perturbation. So that means that this has a very well-defined classical limit. The OTOC, on the other hand, is given by a commutator, and a commutator, if you take h bar to 0, then it won't be anything. So I'm not pretending that the analogy for the time being goes more than formally the way to go and the way that we calculate it. So that's just to, yes? Yes, it's known. So you ask your friend Seligman, and he will give, yeah. Our friend, yeah, it's our friend, but I think you have worked more closely than me, so that's why okay. So, no, it's okay, of course, well known. Okay, you can see that if you average over GOE, you are not going to recover anything like the Lyapunov exponent, because random matrix doesn't know about Lyapunov exponent. So then Seligman has worked and sort of say you have to modify a little bit this random matrix to, and it's always the case, right? Random matrix is completely general, doesn't know about particular parameters, and here is a clear case where we have to put a little bit more. But okay, this is done, this is LOSCHMIDT ECHO. I'm not going to get back essentially to that, but then let's go slowly with the calculations. So again, and this OTOC has been used either with Hermitian or unitary operators, so I chose to have the Hermitian version. And then if you expand, of course, the Hermitian, you have the Hermitian conjugate, which picks up this minus sign. You expand this product, and essentially you collect term, and you have 3 of them. And this is going to be important for what follows, because these 3 terms are of rather different nature. So one of them is the one in which they are intertwined, the A's and the B's. You have another guy in which you have the B square, and this is still different one, because the time, the operator that evolves in time is a square, which means for somebody that has the semi-classical I would say this is 2 trajectory guy, these 2 are 4 trajectory guys. So this is essentially the one that comes up. What about the operators? Well, the operators, they were claimed to be rather general. It's a condition on, they have a condition on local operators that I'm going to come back. I would say that we can think of that just A is the X component of position, B is the X component of momentum. To make it simple, there are things that are going to be completely general, independent of the operator. Others are really specific. So, but anyway, I will move rather soon to this particular choice and the numerics, because we did numerics, or I mean, we have a numerical part of our work, and was done in that case, okay? So, okay, we have these 3 terms that now I compress into this J, and we have to do a thermal average. How do we do a thermal average? We just put a complete basis, and we have the matrix element of each of these guys. Of course, the quantum chaos guys, so condensed matter, when they see the thing, they immediately see that the imaginary part of the green function is popping up, and therefore we can write in this way, and therefore this is more or less the object that we have to handle with. So this sort of matrix element defining here times the imaginary. That's what I was saying is in terms 5 trajectories, because it's a very special semi-classical calculation where we have to handle temperature as well. Okay, so then the idea is, how do we proceed? Well, this needs no introduction, right? So we are going to use the propagator and the green function. Here I wrote the 2-dimensional version of it, because again, we are going to do numerics in a 2D case. And therefore, we start doing the kind of standard things that we do in semi-classical, where to say, well, if I have this ugly expression that I have on the bottom there, it's clear that if there's no some relationship between the trajectories that you are making, then the whole thing, since it's an integral, is probably not going to survive. So one thing is to say that this R and R prime has to be relatively close. Therefore, we know, of course, how to express the green function in that case. And to start with, I start with the free part, and then the periodic corrections can be included later. So there we go. So this is the thing that we had before, and this is just what happens if we put now the free green function. Well, okay, a Bessel function times an exponential can be integrated. So this is the guy that we have to handle. And this is, but this is just for the part in which R is close to R prime. Later we have to come back and do a little bit better job. Now, okay, up to now I think it's okay, and you can follow no problem, so you are the experts. Okay, but let's, as usual, start with the easy guy. Remember that I told you that there's one of these components that is just given by 2 trajectories because the time-dependent operator is condensed. Okay, this I think that it won't be enough to scare you, because also you saw in the talk of our chairman yesterday, he said that this kind of correlators was the most general thing, and he showed something that looked a lot quite like that. Well, the bad news is that later there are even more complicated things that are going to come up, because there are these 4 trajectory guys. And so this is indicated in that way. One important thing is that, okay, you recognize that I just put the 2 propagators, and the terms of locality of the operators is that somehow what I need in this semi-classical calculation, that again I'm sort of specializing in the case of position and momentum, but I need that when this operator acts in my semi-classical expression, I get something that I can identify with the beginning or the end of the trajectory. So this is kind of my definition of local operator, because I must admit I'm not very sure what it is. In our case, it's just like that. It's clear that when we apply the X operator, this is just a X. When we apply a P operator, you can, with 2 lines, you can just get the initial, for instance, this is the initial momentum of trajectory 1, this is the final momentum of the trajectory red, and we call it always the twiddle, the time reversal, because you imagine that what we are going to do is essentially something that you saw also yesterday in our chairman's talk. So we are going to linearize these 2 trajectories around something which is the middle one, and then use, I think it's even the same notation of the kind of center of mass and relative coordinates, and expand the action that will depend essentially of the momentum, the initial momentum of this central trajectory. So this is pretty standard, I would say. And again, if we talk about these 2 trajectory guys, so we have to do these integrals over the center of mass, let's say relative coordinate and final coordinate. And of course, at that time, we do what we have done since the paper of in LOSCHMIDT ECHO, and it's pretty clear, a change of variables in which you make it disappear this coefficient in terms of changing the final position by the initial momentum, right? So this is the standard trick. And this is essentially what we are left with, which you will see we will calculate in 2 steps. Let's say try to get first the higher order in H bar, and then trying to get the corrections as well. So we have, and always we try to separate what comes from the action of the operators. So here is initial momentum, position, and what comes up from this part that comes from the action. This part is the action difference that comes from the temperature that there are. And okay, so this is the nice guy. I'm going to get back to it and sort of calculating, but the bad thing, of course, is that we have to do with the other 2 guys that are 4 trajectory guys. Well, again, I think that if there's an audience in the world that I can show it without being kicked out, is this one, probably not another one, but anyway. So, but also you recognize that this is nothing else. You can even read the pictures, or in the equations, we have the 2 propagators in one direction, the 2 propagators in the other direction, and somehow the trick is going to be, again, the linearize around the mid-trajectory. So this is not very difficult in some sense, so we can use again the trick of center of mass and relative coordinates, and kind of symmetrize a little bit, put in a delta function, and we have an expression that looks alike, and again the kind of canonical change of variables to get something that depends on initial momentum. But now, of course, it's the initial momentum of these 2 middle trajectories that in principle are unrelated. So for the time being, they can be anything they want. What I do need is the one blue and a red to be close to each other. So this is the main thing of the linearization. Okay, so this is as general. Now I sort of go back and say, well, let's take one of them, for instance, the easy guy, and try to get at least the leading order in H bar. So this is the expression that I showed you before, and I go back to the 2 trajectory guy, and I say, well, what do I get in higher order in H bar? Well, in higher order in H bar, we are going to sort of do diagonal in the sense of saying that whatever is not in the argument of the exponent with H bar, I'm going to take it just the same. So that means that that's why I have that the momentum, or the x projection of the momentum final for S2 is, which is minus the one of the time reversal, is just the same thing as the initial one of trajectory 1. So this is a strong diagonal trajectory. And after doing that, then the integration, you put sort of axes that go along the trajectory. It's pretty easy to do it, and so you will say, even deceivingly, and my collaborator were saying, well, what do all this work to get something that is just the thermal average of the operator product? Of course, that has to be like that. So I have the 2 operators that are related with this term O3, and this is the thermal guy. This is what gives the thermal average. So nothing new. Of course, the interest in this following this path is precisely setting the first step to then next the corrections. Okay, so I'm going to spare you the equivalent trajectory for the other, the equivalent procedure for the other 2 terms. However, you may believe, or we may discuss, or you may go to the paper, and then tell you that actually all 3 of them are the same. And this is trivial, in a way, because this is the classical guy, and we know that the OTOC in the classical limit, and especially short times, has to be 0. So that is easy to do, and this is this thermal expression. Well, there are some obvious scalings that you can do, for instance, and that depends indeed of the kind of operators that you have, that this scales linearly with temperature. You can obtain also what is the shoot up from the t equal to 0, and moreover, we can identify the scale in which this expression depends, which is given by the true time that you consider, and a velocity which is actually the thermal mean of the x component. So there's not the factor of 2 that you usually have for Boltzmann. Okay, since we are doing calculations which are perhaps not as reliable as if Alfredo would do it, right? Alfredo doesn't need to go to the computer. We need to go to the computer too. Okay, so this is calculations. So these are done by Nacho Garcia Mata, really an expert in this kind of thing. So let's see what he produced. So as a function of time, but the time is scaled in that way, the three terms. So one of them is just the real part, because the term is not real in general. The other two, it's simply to show that they are real. And with a temperature that is given by this color scale. And then you see that by scaling each component with time, so you have a sort of good data collapsing, not perfect, of course. And however, what you have to take in, you have to realize is this is the quantum guide. So this is the one that comes from a quantum calculation, in which what we just obtained would be the sort of linear order, and for short times. Even for longer time, then you see that it gets a little bit trickier. And then what you observe is this shoot up, which is quadratically, of course, and then a sort of characteristic time that is more or less when you start bouncing, and then a decay. So it's nothing very excited, I would say. So there are some scaling. For instance, this part is mainly exponential, and there are these oscillations that I'm going to talk a little bit more about. But essentially what we come up is to the conclusion that since these three guys are the same, and there was a factor of 2 that you probably forgot but wasn't there, the classical OTOC is 0. And this is rather obvious because the OTOC being a commutator, you would say at least, again, for short times, you don't expect, if you take the limit of h bar going to 0, to obtain anything as they are. Okay, so now, as I said, this was a warm-up exercise that showed that at least at the level of the scaling, we are able to predict more or less how things are, so we can predict these saturation values. There's a whole bunch of things that can be done, but now, of course, the goal is to say, well, what about the leading order? Okay, for the leading order, then we take one of the 4 trajectory guys. We took in this one the O1, and this is essentially the expression that I had before with the 2 trajectories that in principle are unrelated. And again, so it's handling, so we did the change of variables to get rid of these prefactors. And the question is to say, well, how can we do this integration? But now we have to take into account that, okay, these trajectories are indeed different, and therefore, concerning the 2 black trajectories, we say, well, the departure, if I know the initial distance and the difference of initial momentum, I can predict, or I can say, if I'm assuming a completely parabolic simple thing given by a single Lyapunov exponent, that it grows exponentially with time and given by sort of the initial deviation. However, something which is important and not to be forgotten is that can be done provided that the final separation is smaller than the size. So A is the size of the billiard. So it's clear that I cannot pretend to keep on separating once I reach the billiard, and this is essential for the saturation. So you saw that the OTOC saturates and is given in here. Here you don't have just the difference, the 2 trajectories, so you see since you have a product, so it's kind of a second order term, and that's why you get twice the Lyapunov exponent, because you don't have just the difference of x's. Okay, but having said that, you have 2 alternatives. You say, well, I'm either going to perform this integral knowing that I have this cutoff, which I don't know how to do, or you can take the 2 limiting cases of ignoring for the time being the cutoff and getting something that you know at long time is not going to work, or you can just put the cutoff right away and you will have the answer for long times. So let's do the first fair thing, and therefore if we sort of ignore for a while such a cutoff, then we can calculate, then it becomes sort of standard business to calculate this change. Now I'm talking about the change with respect to the case of h equal to 0. That's why this term has been subtracted. And therefore, again, we do things that are rather standard in this trade of going to sort of coordinates along the trajectory and perpendicular to it. And essentially what comes out is something that looks pretty reasonable, I would say. So we do have the H square, of course, that has the problems that we can discuss later. I have an integral over phase space of the initial, that means that you should initial terms, then the exponential form factor, and then a term that depends on the Lyapunov, but the thing is that, of course, that integral over momentum comes from the integral over energy that I have, so we have to include many values of the Lyapunov exponent in a way. So that's the thing to handle. You can show that the OTOC is kind of is related with just one of them, because there are the O1 or O2 that matter, and they are opposite. But what we are interested, if you remember the original prediction, which I said we don't overplay that thing, is to say that this OTOC grow exponentially with the Lyapunov exponent. Well, then we see two things which are not as neat as you could have imagined, and we have to realize that there are two limitations, obviously, to get this exponential. One of them is that the Lyapunov exponent is within a momentum integral. Of course, we know that if this function is smooth enough, if this part is smooth enough and that part acts as a delta function, you can pull it out from the integral. But okay, that has to be seen. It depends on temperature. And moreover, what is more important is that the short and long time parts of the calculation, I know I cannot trust. I sort of insisted in the part of the bound of the exponential increase. So, but having these two things, of course, I go up to, I mean, if I ignore these two things, these integrals are done in a closed form. Of course, they have sort of error functions and things that are not particularly nice, but I have a closed expression with the difficulty, of course, that I have these two limitations. So therefore, if I know that in short time I'm not sure about, in long time I'm not sure about, what I do is to sort of consider this one for intermediate times and do a stationary phase integration, and then I can say that over a given regime, this, I call it low temperature, because I need the low temperature in order for this exponential times the P that comes from the Jacobian in 2 dimensions to act kind of as a peak. In that case, I can sort of show that it's a regime that is exponential with time, and because this was part of the surprise at the beginning when we start playing with it, we say, well, it looks like the Lyapunov, but the Lyapunov decreases with time. This increases, so do we get it? Well, indeed we get it, but in a very peculiar way and in a restricted temperature window. So what do I mean by that? Okay, let's go back to Nacho's calculation. And now this is the OTOC scaled with H square in the stadium that is the same that I show, a quarter stadium, desymmetrized. And the scaling, so it shows that sort of the semi-classical scaling makes some sense, because you see that as temperature increases, what do we get? Well, we get this sort of shoot up that is quadratic. This is trivial. That is something that I must recognize I'm not telling you I'm not able to obtain, because as I say, the short time and the long time are not given by the semi-classics. And then the only thing that we could do, in all honesty, is calculate sort of this sort of intermediate regime with the semi-classical expression that we obtain from the mid-time value of the OTOC. And so this sort of work, and then you see here we do the same thing, but we divide by temperature, and therefore what we observe is that the long times, as I say, the long times I can put in the actually, we were not the first. There was Hashimoto. It's a sort of, I think they are, as far as I know, high energy guys that got interested in the OTOC and did it. And they sort of proved that if you take that two trajectories are immediately at a distance of the order of the size of the billiard, then you get this saturation value that scales with temperature. And then you can see it in here. So if you divide by temperature, you see that the lines scale nicely in there. So it gets, I mean, the two regimes. So, but of course, not everything works in terms of semiclassic. So here is still the same data. I'm sort of using it again and again to show different aspects. So what this curve shows, now it's scaled with what would be kind of the semi-classical prediction, and it essentially tells you that there's a window, now it's in real time. It's a window that in which the exponential holds, but this window progressively gets smaller and smaller as you increase temperature, which is kind of obvious if you think in the integral that gives rise to this exponential increase, so you cannot take simply out of the integral as you did. And for instance, if you scale still with the prefactor, so you can see that you can even put them in a sort of in a window more in a larger interval. However, this coefficient that you need to adjust to scale the OTOC is not something that came out from the semi-classical calculation. So there are many things that can be fitted, but okay, so Nacho kind of, when he sees some scaling, he goes for it, and so it looks nice, suggestive, so it's a weak dependence. So I would say it's something with semi-classics fail, but on the other hand, not so much because it's a log scale. So, and therefore, in that case, I would say that more or less the things that I told you that there's one take-home message. I'm going to get back to it, but just to organize the thoughts, I would say that, okay, exponential growth, yes, but I need relatively low temperature. We will see how much, and not long times. So that means we are immediately, I wouldn't say away of the prediction, but it's not quite that. The growth rate, that is this, I should have said that here when I talk about this lambda g is the geometrical one. That means since we assume that we are in a stadium, then is the one that has the velocity, and it's just a purely geometrical factor. So therefore, since you have that expression in lambda g times the scale velocity, which goes like the square root of the temperature, then you can say that, okay, it's true that this growth rate, that we prefer not to call it Lyapunov because it's not the same thing, it scales with temperature to the 1/2, and of course, comparing temperature to the 1/2 to temperature that is the Maldacena prediction is dangerous, but of course you have to put the right prefactors, and then you see that unless the temperature is such that only the lower states are populated, then of course you put the right constants, and t to the 1/2 is smaller than t, so you would say the bound is respected. So we have this saturation value that depends on temperature, and so as I was saying, this weak temperature dependence of the prefactor, it's something that doesn't come out from the semi-classics. And moreover, what I think it's something that we have not come across to explain decently is this rapid growth, which again is our semi-classic that does not allow us to get to this short time. So this is not, I'm not claiming to have the thing, but okay, this audience is perhaps the most appropriate to give the input for that. Okay, so this is more or less the general thing. I'm going to touch up on, okay, that's perfect. I'm going to touch up on kind of related issues that may be more kind of open ends, and then I'll try to get back to the message I wanted to convey. So one thing is that, of course, for the practitioners, when you have 4 trajectories, you know that you can pair in one way or another, and so you can say that there's something that you can call alternative pairing, in the sense that you can sort of go, then sort of go back, come and pair in these two, and then things at the semi-classical level you can write, and in principle they may look ugly enough, but then when you do the integral stationary phase, then you end up indeed that this alternative pairing is not a new one. So this is a technical thing, but these are, I mean, when you do semi-classics, you kind of go fast and kind of neglect terms, and then you try to be more thorough. And so this is a guy that doesn't put problem. Another one that you may say is, remember that in the green function, I took this r close to r prime, and therefore I say, well, I'm going to take the free green function. And that looks like okay, but of course, for those who know of what, I don't know, was a mild or a large surprise, I don't know, of my good friend Klaus that did it for the conductivity, right? So Klaus had and Felix von Oppen and Greg Hackenbroek, when they were calculating the semi-classical conductivity, they realized that actually you don't really complete a periodic trajectory, which would be the most simple one, but you may have trajectories that sort of go 1.5, and you have 2 stationary phase points to handle. And essentially this term that we calculated in here, so I'm avoiding you the going back to the equation, but you can recognize that these C's are coming from the propagator, so this is, I mean, a time representation, while these D's come from the energy. So I have a mixed time and energy representation, and that's why I say there are the 5 trajectories to handle. However, if you do the stationary phases, you can do it. Of course, it's a little scary because for one trajectory it's dependent on time, for the other trajectory it's dependent on energy, and there are 3 of them. In the case of Klaus, there were 2, so that means you have to open their paper and work it a little bit more. And but essentially, what comes out is an expression that, without really surprise, is similar to what they got for the conductivity, right? So they got a sort of trace formula, except that sort of with the so we have the monodromy matrix and the standard thing, but then a term that in their case was the velocity-velocity correlator, and this is the operator, the 2 operators that we are handling integrated over the trajectories. Those would be the sort of periodic orbit corrections that could explain why at low temperature this curve have this oscillation and didn't go to saturation immediately. One other aspect that we did, and so Diego has been instrumental on that. Diego always worries what may not work, and sometimes I play the optimist, and more often the pessimist, and often he's the optimist, but sometimes he plays pessimist. Then he decided to take the rectangle, and then it's very sober in the message, because in the rectangle, so this is the OTOC, correct me if I'm not saying things correctly, and then we have a growth and something that you may think it's coming up, except that if you look at longer times, then it does this kind of behavior. So there's no saturation in the case of an integrable system, and that has been actually obtained by Yakimoto for the circle as well. So that means that the fact that it saturates, it's essentially the fact that 2 trajectories sort of immediately are all over, and this is not the case by any means. So so I'm almost right in time, 5 minutes. So so this is the 2 things for that we are still trying to understand: the rapid initial growth and the lack of saturation for a long time. And so as a way of conclusion, I sort of go back to our OTOC. I say, well, for us has been very important to consider all these three terms, how they balance each other. So we know that at order H0, so they just are the same. They scale linearly with temperature. So that means concerning to the OTOC, in principle, there's no much. And concerning the quadratic dependence, so we obtain the exponential growth, but I insist that it's in a limited time interval, and this time interval it's strongly dependent on temperature. And sort of that the saturation value is proportional to temperature. So the message is what? The message is that this prediction is sort of work, but not quite, for reasons that we understand pretty much. So this is the message. I say two messages don't hold, but just to put things that Marcos said yesterday, in maps the problem is that temperature is not, there's not an easy way of putting temperature. That's the reason why for short time, so this Lyapunov, then it's easier to extract because you don't have anything like this integration. So this is really indeed, as Marco was saying yesterday, the Lyapunov that you get from the classical map. And in the long time, as he showed, this is related with the way in which saturation is approached is related with the Ruel-Polikov resonances. So I think, okay, with this message and a half, I stop.